Hey guys, Miss Peterson here, and welcome to AP Chemistry Lecture 1-5 on electron structure. Today we're going to be talking about Coulombs Law, electron configurations, the Bohr model of the atom and orbitals, and how all of that creates the atoms that we talk about. This is AP Chem topic 1.5, atomic structure and electron configurations, and in your Brown-LeMay textbooks, this corresponds to section 6.3, 6.6, and 6.8. Okay, so let's start with probably the most fundamental idea in chemistry. If you can really internalize Coulombs' law, you'll be able to explain all of the periodic trends. You'll be able to understand why atoms react the way they do, why they bond the way they do. And it all comes down to Coulombs' law. This law is about electrostatic, the electrostatic force. Okay, that's this one. Now, this is proportional to K. This is just a constant. These are the charges of the two particles, and R is the distance between them. Okay, typically when we talk about this, we're going to be talking about the interaction between the nucleus and the electrons that surround that nucleus. While in AP Chemistry you do not need to be able to actually perform calculations using this equation, in fact, it's not even found on your equation sheet, but it is something that you need to understand conceptually and qualitatively. Basically, as the distance between two charges, distance, increases, the force between them decreases. Okay? But it doesn't decrease linearly. Okay? Because of this squared in the equation, it actually decreases proportionally. You might say exponentially, but it's by the square, okay, the inverse square. So basically, if you, for example, if you double the distance, the force decreases, okay, or decreases to 1/4 of what it was, okay? So if you put the double there, it's squared in the equation, so it's going to decrease by 4 times that, okay? Where if the amount of charge increases, okay, on one or both of them, then the force between the two charges increases proportionately, okay? This is a straight linear or proportionate relationship. Okay, this one was the force with distance. Now if we do the force with charge, it would just be a straight line. Okay, for example, if the charge in the nucleus, we'll say nucleus, doubles, okay, you're going from talking about hydrogen to talking about helium, or going from helium to talking about beryllium. Okay, that charge doubles, the force doubles. Okay, cool. Okay, cool. Pretty straightforward there. So, if we kind of picture this, here we have a Bohr model of magnesium. We know it's magnesium because it has 12 protons and 12 electrons and 2 valence electrons. So which of those electrons would feel the strongest attraction? Okay, well, that's going to be these ones. Okay, I'll mark them with a star. Okay, star would be the strongest. Why? Because they're closer to the nucleus. Okay, so they are going to be held on the tightest. They're going to feel that strongest force of attraction between themselves and the nucleus. Okay, now for the weakest, let me get a different color here. Okay, that's going to be these guys. Okay, and I'll mark those with a circle, okay? Those ones are going to be the weakest, okay? You can call those the valence electrons, the outermost electrons, okay? Because they are farthest away. And, okay, if you kind of picture this atom in your head, you have all of this positive charge at the center, okay? That is your positive charge. But then all of this inner electron cloud stuff is negative, okay? And that actually blocks or shields some of that charge, okay? That is called shielding, okay? And what shielding is basically that the outer electrons are repelled by those inner electrons, okay? They're negative, the inner electrons are negative, they repel each other, and that decreases the force of attraction they experience from the positive protons in the nucleus, okay? And if we want to quantize that, we use something called effective nuclear charge. That is the charge experienced by the valence electrons, okay? So, for example, magnesium's valence electrons, the ones that we circled earlier, experience a Z effective equal to the charge in the nucleus minus the inner electrons. So there's 2, 4, 6, 8, 10 inner electrons. So because protons and electrons both have a charge of about 1, the effective nuclear charge acting on magnesium's valence electrons is only 2. Okay, cool? Okay, cool. So now we're going to talk about the addresses of those electrons. Okay, now in an electron configuration, let's explain what everything means. First, we have these numbers written in superscripts. Okay, now those numbers correspond to the number of electrons in that subshell. Okay, so in the 3s subshell, we have 1 electron. In the 2p subshell, we have 6 electrons. So you're probably like, oh, okay, wait, what subshell, what's all of that? Let's go through it. Starting with the most basic, okay, the electron shells, okay? Sometimes you'll also see them called the energy level. That are these numbers in your electron configuration, okay? They are the most general of the ways that we describe where electrons are, okay? They give you the average distance from the nucleus, okay? So in a Bohr model, we have the n equals 1 subshell, okay? I want that to be smaller. Okay, the n equals 1 subshell, the n equals 2 subshell, and 3 and 4 and etc. Okay? Then, if we want to go one step deeper, we have the subshells. Okay? Now, the subshells are the S, the P, the D, and the F. Okay? They're these guys, S, P, D, and F. And what they refer to specific orbitals or groups of orbitals within that energy level. Okay? Now, the most specific you can get, okay, oh wait. So again, if you're picturing that's the SPDF, the most specific, well, second most specific you could get is the orbital. Now, S subshells have 1 orbital. P subshells have 3 orbitals. Okay? And each orbital fits 2 electrons, okay? One with an up spin and one with a down spin. That's the third level. These are actually what you call the quantum numbers of an electron. And while quantum numbers are a little bit beyond AP Chemistry curriculum, I definitely recommend you read up on them because they're interesting. Okay, so they're the areas within there. S has 1 orbital. P subshell has can fit 3 electrons, so that is 3 orbitals. D have 5, and F have 10. Okay. Now, when we are writing electron configurations, often this is what you're going to see. And now we could figure out who this is based on the periodic table. Okay, this is your kind of cheat sheet for the electron configurations. We have the S block. Okay, we have the P block. We have the D block. And then down here at the bottom, this is the F block. Now remember, these F blocks go right up in there. Okay, so if we're looking at 3s1, that means 3s and 1 electron in that orbital. So that would be that area of the periodic table right there. Okay, and if we then look at our periodic table, that is sodium. Okay, so this is sodium electron configuration. Okay, and another way that you could get that is you can always count up the electrons. 2 plus 2 is 4, plus 6 is 10, plus 1 is 11, and sodium is atomic number 11. So a neutral atom of sodium would have 11 total electrons. Okay, so these over here are called orbital diagrams. They're the most specific way that you could write an electron configuration. You do not need to be able to write these on the AP Chemistry exam, but I want to point out something. Okay, if we look, for example, at nitrogen, okay, it has the 1s, 2 arrows. Each arrow represents an electron. Okay, and then the 2s2, and then it has the 2p3. Okay, now the electrons repel each other. Okay, they're negatively charged. That's Coulombs Law. So they're going to spread out and fill in 1 in each orbital before they will double up. Okay, that's one of the rules of electron configurations. Okay, now to write electron configurations, okay, you can use this little cheat sheet. Okay, and once you've used this cheat sheet enough, you won't even need it. You'll be able to see it just on the periodic table. Now, I want to note something. In general, it goes 1 for the first row, 2s, 2p, 3s, 3p, 4s, whoa, 3d. Okay, d orbitals are really high in energy, and we'll talk about the reasons why in a second. So for that row, that 4th period, okay, groups and periods, that 4th period is actually going to be the 3d electrons. Okay, and then the F goes down even more. It goes 6 and then 4. Okay, so D, you can kind of think of it as n minus 1, and F will always be n minus 2. So let's go ahead and practice writing some of these electron configurations using this cheat sheet. Starting with sodium. Oh, sodium was the one that we had up above, but let me show you kind of where that comes from. We start always from the top. 1s2. Okay, the s orbitals are filled up. Next, 2s2, 2p6, and then we stop when we get to our element, which is in 3s1. Okay, let's go ahead and do selenium. Selenium is number 34 on the periodic table. It is in the P block in group 16, so it is right there. So again, we just start reading out from the top. 1s2, 2s2, 2p6, 3s2, 3p6, okay? Right now I'm right here, so then go down to here, 4s2, now I'm here, go to the D block, but it's 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay? You can use that if you ever forget that the d orbital holds 10 electrons, because it has those 5 orbitals, okay? And then 4p, 1, 2, 3, 4. 4p4. And that's our electron configuration for selenium. Let's do one more. Tungsten. Okay, tungsten is atomic number 74, and you can find it right here. Making sure that these are written correctly. There we go. Right there on the periodic table. 1, 2, 3, 4, 5, 6. Oh, nope. Right there on the periodic table. I was one off. I knew something looked funky. Okay, so this one's going to be a long one. Buckle up, because here we go. Again, I'm just starting from the top and reading across and not stopping until I get to my element. So I got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. Okay, now I'm right there. I'm over here. Okay, I'm going to go on to the next line because I'm running out of room. Or a 6s2. Don't forget about the F block. That is inserted up in there. So after 6s2, electrons fill in the 4f14. Then back to the 5d, 1, 2, 3, 4. 5d4. Okay? Now that was really long. You probably don't want to write that for everyone. So let me teach you condensed electron configuration. And how that works is these noble gases, okay, you might remember that this column is special, okay, those are your noble gases, and they have full outer shells of electrons, aka their electron configurations always end in p6, and that's a super stable arrangement. So we kind of base a lot of our other electron configurations on it. So to write, say, for tungsten, to write a condensed electron configuration, we would go to the noble gas, the row above it, okay? In this case, let me go ahead and write these in. We have helium, and then neon, and argon, and krypton, and xenon, and radon, okay? So it would start with xenon, then 6s2, 4f14, 5d4. So basically, you're saying it has the electron configuration of xenon plus these electrons. For selenium, it would be, it has the electron configuration of argon plus the 4s2, 3d10, 4p4 electrons. Okay, even for sodium, we have, it has the electron configuration of neon. Neon ends in 2p6 plus the 3s1 electrons. Okay, I do also want to point out that while this method of writing the electron configurations is standard, every now and then you will see electron configurations where they keep the D's and like the energy levels consistent. So you might see it written 3p6, 3d10, 4s2. Okay, either way is correct. One's not more correct than another, just another way you might see that represented. Okay, so let's zoom back out for a second and think of which model of electrons gives us the information. Okay, if we have a Bohr model, does a Bohr model tell us the energy levels of the electrons? Okay, remember the Bohr models are the ones that look like this. Yeah, they tell you the energy levels. Okay, that checks off, but they don't have any detail about the subshells or the orbitals. Okay, They don't. You couldn't use a Bohr model to determine where those electrons were. Okay? Where electron configurations have energy level and have the subshell. The orbital you could figure out, but you don't know the specific orbital. You would need the orbital diagram to do all three. Okay? And why would one model be used over another? Why do the different models exist? It has to do with that balance between simplicity and information. If we only need to talk and identify where those valence electrons are, sure, we could do a Bohr model for that. Okay? Typically, we'll use electron configuration. It has that nice medium amount of energy. But if you were studying like specific electrons, you needed to know how many unpaired it had or anything like that, maybe you use the orbital diagram. Okay? Okay, so now let's go ahead and do some practice problems. Okay, let's go ahead. Write the electron configuration of oxygen, atomic number 8. So you're going to go to your periodic table. You're going to find oxygen. And you can see it's 1s2, 2s2, 2p, 1, 2, 3, 4. Okay, 1s2, 2s2, 2p, 4. Or we could have written helium, 2s2, 2p4. When it's just helium, it doesn't make that much sense, doesn't shorten your notation at all. So now we're thinking about how many unpaired electrons does oxygen have. A couple different ways we can approach this. First, we could just sketch out, okay, we have the s orbital and there's 2 electrons in it. Okay, p have 3 orbitals and it has 4 electrons. 1, 2, 3, 4. And there you see you have those 2 unpaired electrons. Okay, cool. Okay, cool. Next one. A certain atom has an ns2-np6 electron configuration in its outermost occupied shell. Which of the following elements could it be? Okay, so np6, that means that it must be at the end of the p block. Okay, it must be a noble gas. It must be in group 18. Okay, also you can see it has 8 valence electrons. That is also a characteristic of group 18. So it could be krypton. Okay, one more practice. We're going to write the electron configuration for bismuth. Bismuth is the element 83, and that is none of your bismuth. Okay, and condensed because, again, we don't want to write the addresses of all 83 electrons. So in your periodic table, you're going to go to the row above, and that is xenon. And then you're going to go past xenon. So that's row 1, 2, 3, 4, 5. Starts in row 6. So xenon, 6s2, and then I have the F1s, which remember go down by 2. So it would be 4f14, 3d, oh, not 3, what am I doing? Okay, 5d10, and then I'm in bismuth in the p block, and it is 6p3. Okay, now if we had to talk about unpaired electrons, again, we're focusing on those p orbitals. Okay, p has 3 orbitals, so that's 1 electron in each orbital, so it has 3 unpaired electrons. Okay, and again, you just kind of picture that 6p, it has 3 orbitals, so 1 electron in each, and none of them are paired. Okay. Now, electron configurations are great, and these orbitals and notations make sense, but what does that actually mean? And that gets a little bit confusing, because in reality, electrons aren't quite orbiting. They're more of a wave of probability, okay? If we were actually going to represent the the s orbitals, we would do something like this, okay? Where a high dot density means there is a high, that is called the wave function. Okay, basically there's a high probability of finding an electron in that area. You will see that often in a graph thing for the sphere. You can see for 1s, you're really likely to find it super close to the nucleus, and then a little bit less likely farther out. For the 2s, there's that little bump, okay, of where you might be likely to find it. And same for the 3s, okay? These little bumps of where are you going to find that electron, okay, based on the distance from that nucleus. Okay, cool? Okay, cool. So, let's go ahead and start to get the idea in our head of how all of these orbitals are shaped. I'm going to show you guys a simulation or a video going through the electron configurations and the shapes of those orbitals. This is the electron distribution for scandium, okay? And scandium is atomic number 21. So this goes all the way up through the d orbitals. Okay? And I'm going to put this video to go a little faster for us. Okay? So that's the 1s. It's a sphere. Again, the center of those axes is the nucleus. 2s is slightly bigger. P orbitals have that sort of infinity dumbbell shape, and there can be one on each axis, the x, the y, and the z axis. Okay? After you fill up those, you go to the 3s, that bigger sphere, a little bit farther away from the nucleus. Okay? Again, the 3p orbitals along each of those axes. There's the 3p sub z for along the z-axis. And then we're bringing in the 4s. Then we bring in the 3ds. Now the ds have this kind of clover-like shape. So they occupy the different planes of the atom. And the more you go out, the funkier they get. So you can kind of picture where these electrons might be based on those d orbitals. Okay? And those are all of the electron clouds of probability densities around scandium. So, p orbitals are those figure eights along the x, the y, and the z axis. D orbitals are clovers, and
Have a look
f orbitals
at the
are
world
just
of cosmos.
Possible Worlds
And
is essentially going to pick up where the last Cosmos series left off.
We're ready to set sail again.
Okay, p orbitals are the dumbbells, d orbitals are the clovers, and f orbitals are just really funky. Okay, now what are some of the rules discovered about how these electrons are organized? Okay, the first main one is called the Aufbau principle. And the Aufbau principle says that electrons are placed in orbitals, subshells, and shells in order of increasing energy. You can see that represented in this graph here. It goes from 1s to 2s to 2p to 3s to 3p to 4s to 3d. So you can see where those energies are like really similar. And that's another reason why we often say transition metals are funky, because the d orbitals and the f orbitals are often so close in energy and close to the neighboring s orbitals. They have a little bit more flexibility in where those electrons are. And that's how you get transition metals that might have a charge of 2 or 3, depending on their environment. Okay? Now, important thing about the Aufbau principle is that there's a lot of exceptions. But that exception is mostly due to the special stability of half-filled orbitals. Because if you have a half-filled orbital, what that's going to do is that is going to minimize electron repulsion. Okay, if you can spread those electrons out more, that could cause some of them to hop into maybe a slightly higher energy level, maybe the 4D instead of the 5S, just to minimize those repulsions. It all goes back to Coulombs Law. So another one, the Pauli exclusion principle, says that two electrons cannot have the same spin. That is represented by those arrows in the orbital diagrams, one upspin and one downspin. And then there's Hund's rule. When an electron is added to a subshell, it will always occupy an empty orbital if there is one, okay? Again, they repel each other. They don't want to double up in an orbital if they don't have to. Now, you guys don't need to know the names of these rules, rather just be able to use their principles to explain any exceptions to the rules that come up. For example, the electron configuration of copper, atomic number 29, is 4s1 3d10 and not 4s2 3d10. And the reason for that, okay, why do you think? Well, if you go into the d orbital, this is a completely full orbital, okay, and that makes it more stable, where this one is now a half-filled orbital. Okay, it is also relatively stable. Okay, if you had them in the 4s2 and 3d9, that's like a almost completely filled orbital. Okay, so these two electrons are going to repel each other enough, and then there's going to be one kind of hanging out over there that's not quite as stable. Okay, and it just has to do with those special stability of the electrons. Okay, spread out electrons to minimize the repulsions, okay? But why would the repulsions be less in a d orbital than they are in the s orbital? You guys tell me. And that is it for our lecture today. Okay, cool? Okay, cool.